So now we're going to go on into section 24.2. We're going to look at reflection at a spherical surface. So we got a spherical mirror here, and we're just going to draw just a little bit of it here on the side. So this has a radius of curvature, and that radius of curvature is going to be R. With its concave side facing the incident light, the light coming in. Okay. So the center of curvature on the surface, or the center of the sphere in which this is just part of the surface, is going to be at C. So in other words, at C, you would draw this thing all the way around. It would be a circle, and its center would be at that spot. So point P is an object point. So for the moment, we're going to assume that the distance from P to V, right here, is going to be greater than R. So the ray PV passes through C. So from going from here to here, it obviously passes through C, strikes the mirror normally, and is reflected back on itself. In other words, this is a 90-degree angle. It's going to reflect back. Boom. So this is called the vertex in the mirror, and the line PCV is called the optic axis. So along the optic axis, what you're seeing is light emitted from here, goes here, bounces, and then comes back through. So that is going to be your optic axis. So as we go through here, what we're going to find out is that the angle that is made here with the optic axis and the value or the ray that's coming out this way, we're going to call it alpha. We're going to call the angle that's made here with the reflected ray that comes through here and gives us point P prime along the optic axis. This is going to be beta. And so alpha plus beta is going to be 2 times this particular angle, phi. And in this particular case, since both the object as well as the image are on the same side as the incoming light rays, then both S and S prime are going to be positive. So this is the construction for finding the position P prime of an image formed by a concave spherical mirror, reflection from a concave spherical mirror. So all rays from P that have a small angle alpha pass through P prime, forming a real image. So we're going to show that all rays from P intersect at the same point P prime as 24.9b. This is right there, no matter what alpha is, provided that it's a small angle. Such rays close to the axis and nearly parallel to it are called paraxial rays. Point P prime is therefore the image of the object, point P. And the object distance measured from the vertex V is S. And the image distance is S prime, just like we saw in the other previous section. The distance from here to here is going to be called S. The distance from here to here is going to be referred to as S prime. So now, again, the object P is on the same side as the incident light. So according to the sine rule, the object distance S is positive. The image point P is on the same side as the reflected light, so the image distance is also positive. So unlike the reflected rays in 24.9b actually do intersect at point P, and then they diverge from P as if they had originated at that point. So this is considered to be a real image point. So a theorem from plane geometry states, in other words, this is a mathematical proof that ends up giving us this. I wouldn't necessarily expect you to derive that, but that information is there if you want it. So when the center of curvature is on the same side as the outgoing reflected light, the radius of curvature is positive. Otherwise, it is considered to be negative. So in other words, in this particular figure, R is positive because the center of the curvature is on the same side of the mirror as the reflected light. This is always the case when the reflection occurs at the concave side of a surface. So for a convex surface, the center of curvature is on the opposite side of the reflected light and R is negative. So here you can see it, the center of curvature on the same side as the outgoing ray, and R is considered to be positive. If, however, we're looking at, just taking this and flipping it around, we would see this coming in here and this going out there. We would say R is negative because the center of the curvature is not on the same side as the outgoing ray. So you have several trigonometric relationships here for 24.9a that if we were to go back through and take a look at right here, we can see that we have a distance h that goes from this line up to this point B, sorry. We have certain right triangles that are made with all of these particular angles, alpha, phi, and beta. And what do all of these mean here? Well, the tangent, well, let me take a step back. H is going to represent the height of point B above the axis, and we're going to let delta denote the short distance from V to the foot of this vertical line. Okay. So let's see here. In other words, this little part right there. So if we make those representations, then we can go through and we can say that the tangent of alpha is h over s minus delta. Does that make sense? Well, the tangent of this is going to be this over this. And again, we're saying that the top part, the opposite part is h. The bottom part is going to be called s. And the reason it's called S is because we're looking at, we want to see this part of the triangle. We know that the total distance here is S, but we know we need to lop off just a little bit of it to get that proper length. And so that's where that comes from. Same type of thing holds here for beta. Beta, again, we're looking at a right triangle here. So we're looking at H here. We know the distance from here to here is going to be S prime. But again, we're only looking for this length here. We call this length delta. So we go through and we lop out that section there by just saying S prime minus delta, and that gives us this length. And so that's where that comes from. Now, phi pretty much goes through and does the same thing. Again, remembering here that phi is at the center of the mirror, the vertex of the mirror. So because of that, our radius, pardon me, the radius of curvature is going to be from here up to here. At any point, that radius is going to be the same value all the way around. And since it's right here, that's why we get the distance from here to here as being R. In order to get the distance for the side of the triangle, again, we lop off delta. So once we have all of that information, then we can go through And we start taking a little bit of liberties here. These trigonometric equations can't be solved simply as the corresponding algebraic equations for a plane mirror. But if we go through and make these angles small, then what we're going to say next is since the tangent of a small angle is equal to the angle itself, we're going to say sleight of hand here that we can replace tangent of alpha by just alpha. Also, if alpha is small, we can ignore the distance delta compared with the others, since the others are going to be so big by comparison. So what we do is we cheat. We take this and we replace it with just alpha. We take this and we just call it S. And we do the same thing for each one of these. If we substitute all of this into equation 24.3 and divide by H, we get the general relationship among S, S prime, and R for a spherical mirror. So let's take a look at 24.3. Well, apparently we can't do that. Let's see. In other words, if we take this equation right here, substitute in all of this mess, this is what we come up with. Now, that equation does not contain the angle alpha, and that means that all rays from P that make sufficiently small angles with the optical axis intersect at P prime after they are reflected. So from that equation, 24.4, as well as others, we consider that to be an approximation. It results from a calculation containing approximations. It makes it easier for us and is valid only for paraxial rays. So for paraxial approximation, it's often used for the approximations just described. The angle alpha increases. If it does, then the point P prime moves somewhat closer to the vertex. Spherical mirror, unlike a plane mirror, does not form precise point image of a point object. This property of a spherical mirror is called a spherical aberration. So now, if R is really big, like infinity big, then the mirror becomes a plane. And equation 24.4 reduces to 24.1, which is S prime is equal to minus S. So the focal point. When the object point P is very far from the mirror, the incoming rays are considered to be parallel. So from equation 24.4, the image distance S prime is therefore given by this, where we go through and replace that with infinity. Rearranging this, this is what we come up with. So we're going to showcase this here in this particular image. A beam of incident rays parallel to the axis converge. In other words, all of these rays that are coming in here, rather than actually be pointing from a particular focal point that's very, very close, since the radius of curvature is actually very, very large, then these rays become parallel. That's the assumption that's made here. So because of that, when they come in and they bounce and they actually hit the spherical mirror, they end up coming together here at this particular focal point. And that F is going to be at a distance of R divided by 2 from the vertex of the mirror. So this focal point or focus and its distance from the vertex is denoted by F, which is called the focal length. So we see that F is related to the radius of curvature through this particular formula. And we can also see that if we have a focal point here that the rays are coming out of and then bouncing out, we can see that that behavior is the same as well as having all these rays come in and focus here, except that the arrows are pointing in different directions. So we can discuss the opposite situation. When an image distance S prime is very large, the outgoing rays are parallel to the optic axis, and the object distance is given by this. So again, we're going to see that the focal length is going to be r divided by 2. So any incoming ray parallel to the optic axis is reflected through the focal point, and any incoming ray that passes through the focal point is reflected parallel to the optic axis. So again, we've got our spherical mirror equation. This comes about from noting that the focal length is the same as r over 2. Because of that, in this particular equation, we just replace that with 1 over f, and that's what we come up with. So for a concave mirror, the focal length is going to be greater than 0. For a convex mirror, the focal length is going to be less than 0. So one element that you can take with you is that if you look at the mirror as a bowl, the concave inner surface of the bowl is reflecting, or the convex outer surface of the bowl is what is doing the reflecting. So let's suppose that we have an object with finite height, represented by this blue arrow, PQ, and it's perpendicular to the axis PV. Then the image of P formed by paraxial rays is at P prime. The object distance for point Q is very nearly equal to that of point P. So the image P prime Q prime is nearly straight and is perpendicular to the axis. Note that the object and the image have different heights, y and y prime respectively. In other words, this goes up to y, this goes down to y prime. And they have opposite orientations. So the lateral magnification, m, as the ratio of image height, y prime, to object height, y, is going to be given. And this looks very much like the formula that we had before. So you can see here that the beige and blue lines are very similar to the lateral magnification, like what we had before. The negative value of m means that the image is inverted. So you can see that is all stated there as well. You've got a problem here that you can work through. You've got a tutorial here that you can work through. I'll leave you all to do that on your own. So those are concave mirrors. Now, what about convex mirrors? So in 2414, the image below, the convex side of a spherical mirror faces the incident light. The center of curvature is on the opposite side from the outgoing rays. So according to the sine rule, R is going to be negative. In other words, you can see it here. R is negative because the incoming rays are over here. So ray PB is reflected with the angles of incidence and reflection both equal to theta. The reflected ray pointed backwards, or projected backwards, intersects at the axis at P prime. All rays from P that are reflected by the mirror appear to diverge from the same point P prime, provided that the angle alpha is small. Therefore, P prime is the image point of P. The object distance S is positive. Since, again, remember, that's on the same side as the incoming rays. The image distance S prime is negative since it's on the opposite side, and so is the radius of curvature. So here we have a construction for finding the magnification of an image formed by a convex mirror. So we've got the reflection as with a concave spherical mirror, rays from P for which angle alpha is small forms an image P prime. So in other words, we got the rays that are coming in here, and then they're reflecting off of this, bouncing them back, they end up over here. Using all of this information, we come up with basically the same types of equations that we had before. So when R is negative, incoming rays parallel to the optic axis are not reflected through the focal point F. Instead, they diverge as though they had come from the point F at a distance, this F, at some focal point beyond the mirror. In this case, F is considered to be the virtual focal point. The corresponding image distance S prime, this right here, is negative, so both F and R are negative as well. And equation 24.5, which is a little further back, holds for convex as well as concave mirrors. So the incoming rays are converging as though they would meet at a virtual focal point F, and they were reflected parallel to the optic axis. Okay. So you got several problems there that I would encourage you to work through, but that's the introduction of the material in this particular section.